So, welcome back. As mentioned, this will be, for some, a recap, for some, more than just a recap, but let's just take it away from there. So, as mentioned, we'll focus on multivariate random variables, and it has some relation to probability theory. So, I don't know how many of you are, you can say, on a DTU bachelor or did your bachelor here at DTU? Most of you. So I will, to those of you who did not raise your hand right now, there will be some questions that are related to, you can say, courses here, just because that gives me a frame of reference. So how many of you have taken an introductory course in probability theory, the 2405? So about half. That is sort of expected. How many have taken, you can say, courses beyond the introduction to statistics and the probability theory course within statistics? Say a multivariate statistics course or something. What have you taken? Just examples. Quick.
Statistical models?
Yes. 2418.
No, not here.
Ah, okay, somewhere else. Yes. Good. So that means that most are at about the same level. You've done some, but not too much. But you can never do too much. I could argue, but that's another story. It's called lifelong learning. There's limits to what you can do within this year. Now, another thing is related to programming and numerical algorithms, stuff like that. I won't make extremely long algorithms, but I will make some for loops and things like that. That's also why I listed Introduction to Programming as prerequisites. I won't get into the epsilon delta kind of things about what is the accuracy of calculations, but I will request that you do some algorithms in some of the assignments, not all. It's kind of the twist between, or the balance between having to implement something on your own gives you some understanding of what is actually going on. Whereas when you use something that someone else implemented, you can get a lot further. And it's always a compromise. And I want you to get both under the hood, but also ride a nice car. So I try to go both ways. Regarding languages, programming languages, what I will use during the lectures is a program called R. How many are familiar with R? For those of you who did not raise your hand right now, what is your preferred language? MATLAB? Python? Those are the two I expected. That's good. Any others? Let me put it this way, that pretty much, I wouldn't say everything, but most things can be done equally well in any language of the three mentioned. There is half of the last assignment that sort of requires R, because there's a library made there that I expect you to use. So there are packages for other softwares that can do similar things, but not the same thing. At least not that I know of. But it's only half of the fourth assignment. And I will, for that particular software package, I will also make, you can say, tutorials on how to do that in R. So, including how to, so it should be code that you can use and get inspired from, and then the rest should be fairly accessible. How many knows more than one of the three languages, R, MATLAB, and Python? Oh, that's good. Because my experience is also, if you know more than one, the next one is easy. Do you agree? At some point it gets like, you just have to figure out when you need a semicolon and how do you make an equal sign, how do you do things in order not to get a compilation failure or something like that. I don't know how many of you are at that stage, but it's, I do not write Python code myself, but I can easily read it. There's some indexing things that is kind of annoying when you're not used to it, but that's kind of the only thing. that is one of the challenges for, you can say, in one of the assignments, I actually request you to hand in a few lines of code. If you cannot read a particular type of code, then we have to work around that. But we'll see how that goes. There are options to get around that. So no problems there. So, as mentioned, this will be a recap. I guess you all have heard the distribution function, density function terms. Many of you may have heard about multivariate normal distribution. Those of you who took the probability theory course here at DTU mostly looked at a two-dimensional multivariate random variable, normal variable. You also heard about the marginal conditional densities, expectations and moments. What I will do here is to kind of do it n-dimensional, most of it. So I want to just define, this is the basis that we're going to use throughout this course. So the first step here is to say, what is the definition of an n-dimensional random vector? Well, it's a vector of elements where each element, oh, could I ask you to close the door? One of you up there. Each element is on its own a univariate random variable. And then you have the joint distribution function down here. F of x1 through xn is the probability of observing each of the xi less than a given number, lowercase xi. So do note the notation. Uppercase variables are random variables. So uppercase letters indicate random variables. Lowercase letters indicates constants. So here is the probability of the random variable x1 being less than or equal to the constant lowercase x1. And if you have a bold symbol, it means it's a vector or a matrix when we get to that. So that's the notation I'll try to use everywhere, like in the book. So we have the joint distribution function again, and then we have the joint density. In the continuous case, basically it's just the partial derivatives of the distribution function to get the density. That's the same in a univariate setting, so there's nothing you can say special about it. It's just to make sure that we have the definitions right. And of course, when you did the partial derivatives to get the densities, you can get back to the distribution function by integration. I assume that's something that you all seen before. Otherwise, either ask a question afterwards or read about it, and then we'll make a discussion about it. But I don't think it's to benefit of everyone to get into further details there. And in the discrete case, well, then you have a probability of observing the particular numbers is the density. That's the change or the difference there. We will mostly work in the continuous case in this course. I will, however, sometimes just mention the discrete cases, just to see, you can say, the transition between, well, swapping integrals out with sums. That's basically what it's all about, to go from the continuous to the discrete case. So the multivariate random normal distribution, the density, probability density function for that. How many of you have not seen that top line there before? A few. That is expected that most of you have seen it before. So the density of x, let me just write it up to have it as reference later on. It's just like the ordinary univariate distribution, except that have an n in here that is the dimension of the variable here, and then you have the square root of the determinant of the so-called covariance matrix out here instead of the sigma. In the univariate case, it reduces to sigma out in here. Then you have the exponential of the usual minus 1/2. And then you have the variable x, that is the function out here, minus mu, that is the mean value of the variable. And then you transpose this, and then you have the inverse of the covariance matrix, that is the sigma in the univariate case you have underneath. And then you have x minus mu on the right-hand side again. So that's the definition. The covariance matrix here is symmetric and positive semi-definite. And we can use the notation x comes from a normal distribution with a vector of mean values and a covariance matrix. And then we have the standard multivariate normal distribution is equivalent, or just expanding the standard normal distribution to say it has mean value 0, and the covariance matrix is the identity matrix of the appropriate dimension. Just like in the univariate case, you can take a standard normal and transform it to any normal distribution by multiplying by a standard deviation and adding the mean value. The only thing is that now we have to do it with matrices. So multiplying with the standard deviation, how do you define that? Well, if we have T times T transpose is equal to the covariance matrix, then we can calculate x equals mu, being the mean value, plus T pre-multiplied on Z, a Z being a standard normal. Then we will have, you can say, the multivariate normal distribution. So the big thing to remember is that you cannot just take the square root of a matrix. You have to do some kind of factorization of it. The same thing applies if you take y to be a linear combination of a constant plus a matrix times a vector of random variables. The distribution of that is again a normal distribution. If x is a normal distribution, like this, it's just you have that the mean value is the constant plus b times the mean value of x, and the covariance, we'll get back to this, is, well, in the univariate case, what you have, if you take a random variable and multiply by a scalar, what is the variance of that? So if you say that in the univariate case, y is equal to a times x, and you ask what is the variance of y? So a squared times the variance of x. Exactly. Now we have the thing about, in the multivariate case, B does not have to be a square matrix. It can have different dimensions. So you cannot just do this. So you will have to pre and post multiply out here. So you pre-multiply by B and post-multiply by B transpose. That's one of the things that you kind of just have to adopt. That's the biggest challenge, I think, from going from the univariate to the multivariate case. That's to just keep in mind which part to transpose. So that's the definition. Just a little bit of teasing. Stochastic variables and distributions. If you have one stochastic variable that is a standard normal and the other one that is minus a standard normal, the distributions, as you can see, are the same, but the variables are different because one is minus and the other one is not. So just to say that even though the distributions are the same, it does not have to be the same variable. Generally, it's only this particular case where it happens. Now, the marginal density function. Do you recall what that means? Yes? Exactly. So what you do is that you say, well, now I'm only interested in, say, the first k dimensions. And then what you do is that you integrate out the joint density function over the remaining dimension from k plus 1 to n. So that's what you do. To show it graphically, basically what you have, if you have a joint density either shown as a 3D plot or you can say an image / contour plot. I don't know how you feel about these things. Now there's no color legend here, which would be making things nicer. But for me, it's very difficult to see anything in a 3D plot. It may look nice, but it's much easier to decode information from a 2D image. I don't know if you agree or disagree. So at least if you're trying to communicate where do you have particular values, make sure that you can actually read it. So what is the marginal density in this case? If I want to have the marginal density of x1, what I have to do is I have to, for each value of x1, I have to integrate out the remaining variables. In this bivariate case, it's just x2. So that means I have to, for each value of x1 here, I just integrate out x2. So what is the integral along the vertical lines in this particular case? That is how you get the marginal density out there. So if I make a drawing of that, x1, x2, now I will make it a little bit more. So what is the difference between the drawing that is there and the one I have here? What have I changed for the distribution from a conceptual point of view? Yes?
The principal axis.
Yes. And from a statistical point of view, how would you, what is more of here than there? Yes?
Correlated.
Yes, so the correlation or covariance is higher in this case. Good. So what happens for the marginal is just to integrate along that line, and then you have the marginal distribution down there. Now, how about the conditional probability? So what does that mean? To condition on something, that means say that given something, then what happens then? So conditional, say if I say that, let me call this, just to get some numbers, so what is the density of x1 conditioning on that x2 is equal to 1 as a function of x1? That's what we're looking into. How do we describe that? So what we're set to do is to look along this line. We condition on us being on this line. So we look at the joint density function of x1, comma x2, where x2 is fixed to 1 in this case. That's what we're doing. Now, there's a problem with this statement. Do you recall what it is? Yes?
Continuity?
No, it's actually, it is continuous, because if you look at it,
Yeah, oh yeah, no, sorry.
I'd only draw the contour lines up here. If I plot, maybe I should do it with red again. Place it there. That is the joint entity, how it looks along that line. Why can't I just use that as my density here? It goes back to the definition of what is required for something to be a density or distribution function. Exactly. The integral along that line is not 1, because what is 1 is the integral across the entire surface. Now we just make the integral along one line. So how do we normalize it? Well, if you need it to be 1, you just divide by the integral along that line. So what you do is that you take the marginal density of x2. So say, what is the probability of being at x2 equals to 1? Then you make the integral along that line for the marginal distribution along that line. So if you take all the values along that line, that is the joint density up here, and divide it by the integral along that line, that's the marginal density. The integral of this along that line will be 1. So now what happens if we, instead of doing it down here at 1, do it up at 3? Then we get something that looks like that. But the important thing is that we have to just remember to normalize. So that's what I've shown, except for the numerical values out there are different. I have the joint density divided by the marginal density at the value where you fix it. That is the conditional distribution of density along that line. And just showed for 2 values, similar to what I've done up there. So that's one thing that we're going to do a lot. Not doing the integral as such, but the concept of condition. So the expected value depends on what you condition on, which value you condition on, right? And that was why I kind of increased the correlation over here, that's to see a larger shift when you condition on different values. So, next to marginal and conditional densities, what is important is to understand independence. So, if knowledge about x does not provide any information about y, then the conditional expectation of y given x is just the marginal distribution of y. Because if there's no information from x, it doesn't matter if you condition or not, you get the same. So it leads to the following definition, that if the joint density is the product of the marginal densities, then they are stochastically independent. So if the joint density is the product of the marginal densities, then they're independent. So that means that this expression up here should hold both ways. X does not provide any information of y, and y does not provide any information on x. The expectation is also something that you've seen before, I assume. So in a univariate case, the expectation of x, the stochastic variable x, is the integral over the outcome space, say minus infinity to infinity, of x times the density of x in a continuous case, and in a discrete case, it's just the sum instead of the integral. So it's the sum over all possible values. One thing that is important to remember is that expectation is a linear operator. I mean, you all know that if you have an integral of a plus b of something, you can do the integration of a separate from b. That's the same thing here. It's not new, but it's a different way of doing it because I do not expect that you will write up the integrals every time. I expect that you know that the expectation is basically doing an integration and using that information, well, it is linear, so we have the usual calculation rules for integrals, we can use them here. So don't write up all the integrals, but just know what is behind the scene. So the expectation of a sum is the sum of the expectations. And the expectation of a constant, that is just a constant. The expectation of a constant time a random variable, well, the constant, you can move that outside. So the expectation of b times x1 is b times the expectation of x1. So often it's the case that if you can get to expectation of just the random variable, then it's easy, because that's what you will know typically. Whereas the expectation of something complex expression, that's more complicated. So the expectation is what is called the first order moment. Now the second order moment, basically it's again an integration. The second order is x to the second power, but you can also do the nth order moment. That is the expectation of x to the nth power. And it's basically the same thing you do. You take whatever function of x in here, you place that onto the integral sign, integrate over the entire space, where you take your expression and multiply that by density. Then we have what's called the central moment. Central means that you subtract the mean value. And that's basically what you do in here. You say the expectation of x minus the expected value, namely the mean value, to the nth power. And what we typically know is the variance, which is the second central moment. And we don't want to say that all the time, so we'll just use the word variance. Now, I assume that many of you have seen this before. So the definition of the variance is the expectation, it's the second order central moment. So it's the expectation of x minus the expectation of x square, because it's the second order. And then there's this calculation rule up there. I don't know how many of you remember the reasons behind that, so that's why I'll just do it. So we have the expectation out here. It's just an integral. Then you have what is in here. We can just multiply that out. So we have an x squared, and then you have the expectation of x squared, and then you have minus 2 times the product of the two, 2 times x times the expectation of x, and then we have an expectation of all that. Now, if we go through these, it's a linear operator, the expectation. So I can do the expectation by terms. So that's the expectation of x squared plus, well, the expectation of the expectation. That is the same as the expectation. So that is the expectation of x squared minus, a constant goes out. The expectation is also a constant. Expectation of x is a constant in this case. So what is left is the expectation of x in there. So effectively, this becomes the expectation of x from that x times the expectation of x that was already there as a constant. That there is, of course, the expectation of x squared, as is also there. So keep the first term, and then we have plus 1 expectation of x squared and minus 2 of those, so we end up with minus the expectation of x squared. So that's the proof of that relation up there. The variance of x is the expectation of x squared minus the expectation of x squared. It's one of those things that are very difficult to say without having the verbal parenthesis there. But that's how I try to remember it. So going from variance, the next step is covariance. And the covariance of x1 and x2 is sort of the same definition as we have for the variance here, except instead of having the square here, we just take the separate terms. So we have the same variable minus expectation of that variable for the first part of the covariance and for the second part. So the covariance of x1 and x2 is the expectation of x1 minus the expectation of x1 times x2 minus the expectation of x2. And we can make a parallel calculation to this, where what we actually find is that the covariance is the expectation of the product of the two minus the product of the expectations of the two. You can see that if you plug in x1 and x1, or just x, well, that is x squared, and this is the expectation of x squared. So, as comes from the definition that the variance of x is the covariance of x comma x. Now, this expression here doesn't look so nice at first when you look at it, but it can be used to solve pretty much any case of problem that you will meet. So it's good to have at hand. Often you won't have 4 different stochastic variables in here. You may have, say, as in one of the exercises today, you have an x1 and x2, and an x1 and x2, or an x and a y, whatever. But you can, the good thing here is you remember to get all the different terms in here. I used the good old classic rule here to get the 2 there, but essentially it comes from 2 separate terms. If I multiply everything out, it's the first with the second and so forth. At first with the first and first with the second, and likewise for the other element. And that's what you get in here. In this case, the constants are scalars. Notice they are lowercase numbers and they're not bold. So therefore, they can just be moved either in front or on the back. If they are not scalars, we have to keep track of where to place things, as we saw previously. Just recapping, basically that one up there, the variance of a constant plus a constant times a stochastic variable, well, the variance of a constant is 0. So what you're left with is you can ignore the a plus part here, and then you just have exact same thing as listed there. The constant goes outside squared when it's a scalar. If it's not a scalar, if it's a matrix, well, you have to pre-multiply with that and post-multiply with the transpose. You'll get to that. So, that was a little bit about moments. When you talk about a moment representation, say a second order moment representation, which is what we typically would do in this course is that since we're looking at normally distributed variables, what we're caring about is the mean value and the variance covariance structure. So we care about things up to the second order. We don't care about higher order moments because there's no information there. We have all the information that we need in the mean and the covariance structure. So we have the mean, the variance, and the covariance if relevant. That means if you have a system where the dimension is higher than 1, then you need to keep track of the covariance as well. Now, that was the univariate case. Now we'll quickly do the same thing in a multivariate case. So the expectation of a stochastic vector is the expectation made for each element. That's fairly easy to grasp. The tricky part is for the variance covariance matrix. The variance of the stochastic variable, multivariate variable x, is the expectation. The structure is the same. The problem is you cannot take the square of a vector. It's not well defined. You know what the dimension should be. If you have a two-dimensional variable, the variance covariance matrix should give you both the variances and the covariance. So you need a 2x2 matrix. So you have a column vector, and then you multiply by the transpose, and then you get a 2x2 matrix in a two-dimensional system, but it expands to the n-dimensional system. So we get this matrix where each element is either in the diagonal, you have the variance of the univariate variables, and in the off-diagonal elements, you have the covariances between the corresponding univariate variables. So that's the definition. And notice the covariance of x1, x2, and then you have the covariance of x2, x1. So what holds for those two numbers? Covariance of x1 and x2, and covariance of x2 and x1. They are the same, exactly. I heard it from a couple, so that I hope you were going to say the same. So it's a symmetric matrix, so therefore they have to be the same. So correlation, often you talk about correlation rather than covariances because it's easier to see how close things are to 1 than it is how close things are to some global variance. So we tend to often normalize things and look at correlations instead of looking at the covariances when we're comparing things. And the correlation is the usual definition. It's the covariance between xi and xj divided by the square root of the product of the variances of xi and xj. And there is a kind of interesting thing. It's a notation tweak that you will see sometimes. What you have there is sigma ij. What is that? That's a covariance. Sigma ij is the covariance between, in this case, xi and xj. Sigma I, well, that is the square root of the variance of xi. That's the traditional thing that you're used to, right? Now, one thing that you'll see some places is sigma I. What is that? Now I heard two different answers. One said correlation, the other one said covariance. Or variance, exactly. It is the variance because you're actually using this indexing. So it is the covariance of xi, comma xi, which is the variance of xi. So removing an I here corresponds to taking the square root. That's what I call tricky notation, but you will see it. So that's why I just... Now you have seen the link. So now you can use it when you are exposed to it. Not if, but when. So, correlation and independence are two things that you have to just say things right. So if two stochastic variables are, say, x and y, if they are independent, then the covariance is equal to 0. If the covariance is 0, the correlation is, of course, also 0. Now, you can also do the other way around. Let's just x be a standard normal distribution, and then you take the covariance of x and x squared. If you do the math of that, well, you have to just take the expectation of x times x squared minus the product of the expectations, and you end up with the expectation, because this expectation here is 0, you're left with this term here, that is the expectation of x cubed, that is 0. Now, what does that mean? It means that the correlation and covariance is 0. Are they independent? No, they're not, because you get from one to the other by squaring it. So, lack of correlation does not imply independence, but independence implies 0 correlation or covariance. So it's important to say that does only go one way. It's a one-way street. In most cases, it will hold both ways, but not all the time. It depends on how strange constructions are made. Like the one here with x and x squared is to some extent a strange construction. So whenever you have nonlinearities, you can find weird things as well. Again, univariate, we go multivariate. Expectation and variance. So what we did was the expectation and variance. We also need to do the general covariance. So now x and y are both stochastic vectors. They don't have to have the same length. But the definition is the same as in the univariate case, or for the covariance. It's x times mu times y times nu as the mean value there. And then you just need to remember the transpose in here. And that means that you get a covariance matrix where each element are the corresponding univariate covariances. Now, what happens here? Is this matrix symmetric? There's a 50% chance of a right answer.
No, it's not necessarily square, so it can be.
It doesn't necessarily square, so it's quite easy to answer that. by default, it's not symmetric. Only if you do the covariance of x and x, then of course it will be, because then you have the covariance matrix of a standard, or of a normal, of a single variable. But when you do it in between two, it's generally not. There are more calculation rules related to this in the book. I think the most important thing is to expand up here and say, well, when you have it as a vector, the variance of a matrix A multiplied on X, that's where you say you pre-multiply by that matrix, and then you have the variance of X, or covariance matrix here, and you post-multiply by A transpose. And if you look at it a little bit closer, I recommend that you do that. What if the dimension of if A is not a square matrix? That means that the outcome here, the variance of Y, has a different dimension than X. Then please just verify with yourself that having it with the transposes this way means that actually it does fit. It does always work like that. This is one of the slides that I remember the first time I saw these expressions. And like, why do I need these? Later on you realize because it makes life easier. So these are some relations. Starting from the conditional expectation, the definition of that, well, it's just like the conditional distribution or density. Because the expectation is an integral. You just have to specify what is the density function that is relevant to use when you're doing the integration. And when you do condition, well, of course, you use the conditional density as written over there. So that's fairly easy. But again, let's not do all the integrations. Let's just learn how to do calculations with the expectations. So, if x and y are independent, then the expectation of y conditional on x is just the expectation of y. That's fairly easy. That is the same as saying if they're independent, then the conditional distribution is equal to the marginal distribution, just as a definition that we had for independence previously. Now, the expectation of y, you can write that as the expectation of y given x. This is one of those where you say, well, why do you want to overcomplicate things? But often, if you have two random variables, or you can decompose your problem into two variables, then you can say that, well, if you know what x is, then y is easy to calculate. So in doing this means that, and one thing to keep in mind is that the expectation of y given x, this is also a random variable because I have not defined what x is. In the integral up there, I define x equals to lowercase x for a given value of x. But here I have not defined which value of x I condition on. So this is still a random variable. But when I do the expectation once again, that expectation is actually with respect to x. So it's x that I'm integrating out. The next one, well, if the expectation, since this is a random variable, well, when you condition on g of x, condition on x, when x is given, that is just a constant as such. And constants can be moved outside. It's still not a real constant, it's a random variable, but it doesn't change anything in here. So you can move the function of x outside and something when you make the condition on x, because it's still just a random variable. If you want to get rid of x again, you need to do once again an expectation as you did up there. The expectation of a product of g of x and y, well, here you can take y and make that an expectation of y given x. Why is that nice? Well, it's nice because this here is a function of x, and that is a function of x. So all of a sudden you had a univariate distribution in the inside, where you started off with a bivariate distribution. So it means, again, if you have an easy connection between x and y, then you can kind of make things easier by using the conditional expectation in there. Now comes an easy one. The expectation of a constant given whatever is a constant. A constant will always remain a constant. And the expectation of a function of a stochastic variable given that particular stochastic variable is just a function of that stochastic variable, because it's still a stochastic variable. And then we have the linearity of the expectation, of course, also works with conditional expectation. So you can take these, you can say expectations by parts. Basically, it's the same thing up here. Remember, it's an integral. If you have a sum of different terms, you can integrate them one by one. So the expectation of a sum is the sum of the expectations. And you can take a constant and move it outside. That was a lot of words, I know. But keep that one in mind. Of at least you have to know where it is, how to find it easily. Now we'll take the next mental step up. It's all related to the same story about if it's easy to describe y when we know x, then we'll look at the conditional distribution. So when you have the variance of y given x, well, we can do the same, exact same, and this is also multivariate. It kind of covers the whole thing. It's the expectation of y minus the expectation of y given x times the same thing transpose, because it's a variance. And then we have the condition of x out there. And the covariance, it's the same thing. All you do is that for the second part, you just swap the letters. So you have, for the first, the covariance of one variable, the y, goes into the first term, and the second variable goes into the second term. And when you condition it out here, well, you just keep that conditioning everywhere. You would have an expectation, you just keep that condition. The variance separation theorem, that's the tricky part of it. Because how do we use this? As I said, when it's easy to do the calculations, if you know the relation between y and x, then the variance of y is equal to the expectation of the conditional variance of y given x plus the variance of the expectation of y given x. It's quite easy to remember. It's the expectation of the variance plus the variance of the expectation. It takes a little bit longer time to understand what it actually does to it. And the covariance is the same way. It's the expectation of the covariances, conditional covariances, plus the covariance of the conditional expectations. So the covariance is always just the same structure as the variance. We just have to kind of keep track of what is the first and second element. Okay, now to something slightly different, but yet again, the important part, because this is what you're going to be doing repeatedly. So linear projections. I guess you've all done that, because whenever you do linear regression, that's essentially what you do. And how we will define it, if we have two vectors y and x, we look at the expectation of that. It has the variance structure like this. So you have the variance matrix of the two multivariate random vectors here, and then you have the covariances in the off-diagonal parts of the matrix. Sigma xy and sigma yx. Can you guess what holds for those two? They're not equal, but close to. The full matrix here has to be symmetric. So one is the transpose of the other. Otherwise it's not symmetric. Anyways, we'll get back to that later, but now just to keep it in mind. So we'll define the linear projection of y on x as the mean value of y plus the covariance matrix between y and x times the inverse of the variance of x times how far is x away from the mean value of x. So what is this? Well, we'll see how it works later on. If we look at this definition, we often end up in a case where you can write it as a constant plus another constant times x. So it is just like a linear regression kind of thing. There's one huge difference to what you've done a linear regression previously. I'll just say it now, but you'll probably get it later on. When you do linear regression ordinary, you say that the x as your predictors, they are known with no uncertainty. Whereas in this case, your x also have a covariance. That's a big difference. So when you do linear regression, what you do is that you reduce the sum of squared residuals in a vertical sense. When you do projection, you have another direction where you fit your model. Because you account for you have both variance in y and in x. And that's kind of that's a big difference here. And if you look at the variance of your observations y minus the projection of y on x, you get it to be the variance of y, and then it's reduced by something. And how much it is reduced depends on how large is the covariance between x and y. So you have things that have a high covariance or correlation, then you get a large reduction. If not, you get a smaller reduction. That makes intuitive sense. However, the covariance of the what I will call prediction error and your x being your predictor is 0. So you do something that is the best that you can do. So if we just recap the definition, rho x y equals to mu y plus sigma y x, sigma x x inverse, x minus mu x. That's the definition of the linear projection. Then if you take the last line down there and we want to look at the covariance of y minus rho x of y, have the covariance of that with x. Well, the first thing to do is to just plug in this term that we have defined up here. So it's the covariance of y minus mu y. And then because that minus, that we get a minus up there, minus sigma yx, sigma xx inverse, x minus mu x, comma, x. Now, remember it's a linear operator. The expectation, and we only have one term over here. We have the calculation rule of a plus b, comma b plus c. So you have to do all terms individually. The first thing to look at it here is how many constants do we have here? Two. Essentially we have 4, but it reduces to 2. So there's no contribution from the mean value of y, and the covariance and variance matrices are constants, and so is mu x, so there's no contribution from that one either. So this reduces to the covariance of y minus sigma yx, sigma xx, and sometimes my sigmas are a little bit sloppy, inverse on x and x. Now we can look at the two different terms here individually. And you can say the covariance of y and x, that's an easy one. And then we have the covariance. Well, these are constant, right? So we can move those outside. In this case, they're only on one element, on the first element, so they go outside on the left-hand side without being transposed. Sigma yx, sigma xx inverse, and then the covariance of x and x. This here is sigma xx, right? Sigma xx inverse pre-multiplied on sigma xx is what? They are symmetric. So that's the identity. So we're left with, and this one here is sigma yx, and then we have from over here we have sigma yx, and the rest is the identity. I don't have to write that. So sigma yx minus sigma yx. That's a big fat zero. That's where we wanted to get at. Here comes again the tricky part. Conditional means and linear projections. Well, what we do here, it minimizes the variance among all linear relations that gives projection errors that are uncorrelated with x, that we just proved down here right now. If x and y is multivariate normal with a property of the expectation of y given x, then nevertheless, if we have the same constructed case as before,